How to find the majority element in an array. So you may be thinking that it's a very simple problem. Why I have put two fires here? So indeed, it's going to be a hot discussion. So let's stay tuned for this. I will start with trivial solutions, like we will be using unordered map, then we will use sorting trick, then we will move to non-trivial method of solving it, which will be a space optimized method of solving this problem, and that will be order 1 space and order n time complexity. And this has been a hot question for some of the major interviews. So let's see. Let's start with the trivial solution. First, understand what is the majority element, what is meant by majority element. So you are given an array, and here there will be different values in it, but one of the values will be occurring more than n by 2 times. So count should be more than this. So if n is even, let's say 6, there are 6 elements, then its count should be, this value will be 3, so its count should be 4. That is more than half. If n is odd, then n by 2 will be 2, so more than that will be 3. So if we have 5 elements, then it should occur 3 times. At least it can occur 4 or even 5 times. And if it's 6, then it should occur at least 4 times. So always more than half. Now in this example, what you see, 3 occurs 3 times, 2 occurs 1 time, and 1 occurs 1 time. And total count was 5. So 3 is a majority element. And there may be possibility of none of the elements being majority element. But for this lead code problem, they have given that, assume that there always exists a majority element. So what can be the most simplest solution that comes to your mind? You iterate this array from left to right, keep track of count of each elements. We can put that in a map having int and int. Key is int, which will be the actual element, and the second, the value will denote the count. So first time we insert it into the map, we insert it with a value of 1, and later if we find it in the map, then we increment its count. And whenever at any point of time, let's say we have reached till here or till here, we see that the count of 3 is already 3, and we beforehand know what is the size of the array. So if at any point of time count of the element goes more than n by 2, we return that element. Let's say we are processing index I at that point. So we return nums I straight away because we don't need to check further. The array length is, let's say 10, and we had already encountered a count of 6 by the time we reach some index like 6 or 7. So we see that already we have achieved the majority index. We don't need to look further, and we return straight away. And if we don't encounter any such situation, so if there is a majority element, at least when we are processing the last I, the count of that after inserting the map should be more than n by 2. So if we don't encounter a situation like that, we return some other value like -1 or something. But here in this problem, we will not need that. So this would be our first approach. What will be the time complexity? We do one iteration of this array. So time complexity is order n, assuming the find and insert all operations in the hash map are O1. So it will take order n time, but we also need On space for it. So space is also On. So both are On. Now there can be another trick. So what happens if I sort these elements? So if we sort this input array and a majority element always exists, it's given. So there can be 3 scenarios. So if you sort the array, maybe the majority element is the smallest. So it will start from here. And since its count is more than half, so if this is the middle, it will go at least till middle plus 1. If it's the largest element, then it starts from here and it will cross middle -1 element in that case. And the second situation would be that it starts somewhere here. It cannot start after middle plus 1. because if it first occurs after middle plus 1, then how can it be? There are only middle minus 1 spaces left, so its count can never be n by 2 or more than that. So it has to start in the first half and then it will continue in the second half. So in all the three cases, the middle element, if you see, has to be the majority element. So let's say you are allowed to sort the array, the original array. So you will sort it and you will return the middle element. That will be the majority element. So what is the time complexity here? Sorting the array will take n log n time, and then returning the middle element is order 1 time. So this is the time complexity. And space, let's say we are allowed to modify the original array, so we don't need any extra space. So this is the space. So we have improved the space, but we have deteriorated on time. So this was our first method using hash map. This is our second method using sorting. So each of these is better in one of the aspects in terms of space and time. So can we achieve the best of these two? So what is the best of time among these two? It's O of n. What is the best in terms of space complexity? It's O of 1. So can we achieve this, both of these? So that's where Moore's voting algorithm comes handy. So let's see what is the algorithm. It says that if you are given an array and it has some majority element in it, and you start with first index and you assume that that is the candidate majority element. You don't know yet, but you assume that that is the candidate. And you keep track of one index, and this array is, let's say, A. So that means A of IDX is the candidate element, and you keep track of a count. So count is initially 1 because this element has occurred once here in the beginning. Now there are a few scenarios. So whenever we iterate this array and move to next element, if it's same as the current candidate, this is the candidate, then we increment the count. So it strengthens our belief in this number being the candidate majority element, because we have encountered another instance of this. But if we encounter an element which is different from that candidate, we decrement the count. So what will happen? Let's say either this first element was a candidate or was not a candidate. So if this C occur a few times, then the count has become 3. Then we encounter other elements and the actual candidate element, and somewhere its count will become 0. If the C is not a true candidate, if we follow this mechanism, somewhere its count has to decrease by the time we reach the end of the array. If the count does not decrease to 0, below 0, then that means this was the actual majority element, because we started with 1, and when will it not decrease to 0? Whenever we encounter the same element, we increment its count. So its count becomes 2, 3, 4. Whenever we encounter a different element, we decrement its count. So whatever was the actual majority element, that will occur at least n by 2 plus 1 times. So that should have decremented this count to 0 even before reaching the last element. So if the count does not reach 0, that means C was the majority element. That is the best case. And if the count does not become 0 from beginning till end, that means this has to be majority element. Because in order to offset its count, it needs at least n by 2 plus 1 other elements. Because that is the case when we decrement the count. If we encounter same element, we increment the count. So that is one case. But if it's not a candidate element, then somewhere its count will reset. Count will become 0. And when count becomes 0, we reset our belief. We now believe that our assumption was not correct or not strong enough yet, and our count has become 0. So let's take a new candidate. So let's say it resets here. That is, count was positive till this point, but when we reach this element, we encounter as many different elements as many C. So there are, if this length is x, then this will be n minus x because there are total n elements. So this means that by the time we reach this, we have iterated this x elements, count has come back to 0. It may come back very next step at second also. This is a very general scenario. I'm taking x. If C is not a candidate, its count has to come to 0. So if the count comes to 0, what this means? Still C can be or may not be the majority element, but whatever is the case, C has occurred x by 2 times, and other elements have also occurred combined x by 2 times. So if C was majority element, in this part of the array, what will be the count of majority element? So either the majority element has occurred x by 2 times or less than x by 2 times. It cannot occur more than x by 2 times because the count has just become 0. So what is going to be the count in remaining part of the array? This part we have explored, this part we have not. So what can be the maximum count of actual majority element here? X by 2. In fact, equal to or less than x by 2. So in this part, it will be n by 2 plus 1. This was the original minimum count of this. So at least more than this, minus x by 2. So the count of majority element has to be more than this in this part of the array. It will be. And what is the count of the original majority element in the remaining part of the array? If any element has a count of more than n minus k by 2 plus 1, then that will be a majority element. Or it's x rather, not k. So it can be written as n by 2 minus x by 2 plus 1. And you see that the count of majority element is more than n by 2 plus 1 minus x by 2. So it satisfies the condition. So whatever was the original majority element, that will still be a majority element in this part of the array. And again, we repeat the same logic. We pick a candidate, and if its count never becomes 0, that means that is the majority element. We return that. But if its count becomes 0 somewhere, then again, by the same logic, we can eliminate this part of the array, and whatever was the majority element will still be a majority element in this smaller part, the remaining part. And ultimately, let's say we reach last 3 or 5 or 4 elements which are not, and we have not picked any other majority element. Then in the last 4 or 5 also, it should occur, let's say it's 5. Then it should occur 3 times. So for 5 or even smaller, you can even list down different permutations. What can be the possibilities? It can occur like C, 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 some other element. Then if we start from here, we will never reach a count of 0. If it's like C, X, X, C, C, then here we reach count of 0. We reset it with new candidate. Count becomes 2, then 1, then 0. We reset it and count becomes 1. So in any case, it has to return the candidate element. You can break it even further. So here it becomes 0. So we eliminate this part. Again we start here. Here its count becomes 0. So we eliminate this part. So whenever it's reset, you can ignore that part, and that original majority element will be majority element in the remaining part as well. So that's the logic. So let's implement all the 3 methods and we will do it in C++, then Java, and finally Python. So first let's do that unordered map thing also. Counts if it does not exist in the map, insert it with a count of 1. If it exists, increment its count. And if at any point of time counts n is greater than nums dot size divided by 2, then return n, and it will at least be true at the last index. Otherwise we can return -1, although it's given it will not happen. You can see, assume that the array is non-empty and the majority element always exists. So it will never reach here, it will return beforehand. So it works. Let's submit. And the solution is accepted. Now we will write the second method, that is sorting. So we will do sort, and we will modify the original array itself. So we have sorted it, and then we return nums dot size divided by 2. So the middle element will always be this majority element, and we had seen the explanation why. And this solution is also accepted. Finally, we will look at the Moore's voting algorithm. So int idx equal to 0. This is the index of candidate majority element, and count is initialized to 1. And we will start from first index, I equal to 1, because 0 we have already assumed to be candidate and count to be 1. So we have accounted for that. So we start from next element. If nums I equal to nums idx, that is candidate, then we do count plus plus, else count minus minus. And if count becomes 0, then we reset. So whatever was our earlier assumption of candidate, we have encountered exactly same number of non-candidate elements as the assumed candidate elements. So this is the case when count becomes 0. Then we reset the new index to be the current index. That is, the current element becomes the new candidate. And whenever this reset is happening, we are ignoring that from beginning till that part of the array. And the original majority element still remains the majority element in the remaining array. And ultimately, it will never reach 0, this count, by shrinking this. And finally, we have to return idx. So if this count never became 0, idx will never change, and that will be the candidate. Some issue here, runtime error. And it works, so let's submit. And this solution is also accepted. So this was an optimized solution. It may look difficult. You should go through the explanation multiple times and try it yourself. Then the explanation will be clear. It's not very trivial to understand it. So I hope you enjoyed all the three solutions. Oh, I forgot to implement it in Java. So let's implement this last one, the Moore's voting algorithm in Java. Nums dot length. Hopefully this should work. And it works, so let's submit. And it's accepted in Java. Now we will do the same thing in Python 3. For I in range from 1 to so this works here, so let's submit. And the solution is accepted in Python as well. So I hope you enjoyed all the three solutions, especially the Morse voting algorithm, which is very non-trivial. And considering that this problem is marked as easy, it's not expected to solve it using the Morse voting algorithm, but it's good to know this is a very nice approach.